All machine learning algorithms explained, starting with supervised learning. Supervised learning is the most common branch of machine learning. At its core, it's simple. You train on labeled data. That means every input already has a known output. The algorithm's job is to learn the mapping between them. Once trained, it can predict outcomes for new, unseen inputs. Within supervised learning, there are two main subtypes: regression and classification. Regression is about predicting continuous values. If you feed the model housing data like size, location, and number of rooms, regression can estimate the price of a home. Linear regression is the classic starting point, drawing the best fit line through data points to predict values. More advanced options include decision trees and support vector regression, which handle complex patterns better. Classification, on the other hand, predicts categories. Think of email spam filters. Each message is labeled as spam or not spam. The algorithm learns the rules and applies them to new emails. Logistic regression is a simple but powerful classifier. Support vector machines can separate categories with a clear boundary. K-nearest neighbors classifies by looking at the majority label of nearby data points. Decision trees can split inputs step by step, making results easy to interpret. When should you use supervised learning? Anytime you have historical data with clear outcomes. Predicting stock prices, detecting fraud, recognizing handwritten digits, or diagnosing medical conditions are all supervised learning problems. The strengths? Super obvious. Supervised learning is highly effective when labeled data is available. It can reach high accuracy, provide clear predictions, and is flexible across industries. But there are drawbacks. Getting large, high-quality labeled data sets is expensive and time-consuming. Models can overfit, memorizing noise and training data rather than learning real patterns. And if the future looks different from the past, predictions may fail. In short, supervised learning powers much of the AI we see today. From recommendation systems to voice assistants, it's the backbone of applied machine learning. But its success depends on one thing: labeled data. Without it, the algorithm is blind. But what happens when the data comes with no labels at all? That's where unsupervised learning enters the picture. Unlike supervised learning, there's no teacher, meaning the algorithm doesn't really know the right answer, and instead, it searches for hidden structures and patterns in the data on its own. And there are two major subtypes: clustering and dimensionality reduction. The first one is clustering. It is all about grouping similar data points together. The most famous algorithm here is k-means. It assigns data points to clusters by minimizing the distance to each cluster's center. For example, a retail company might cluster customers into distinct groups based on shopping habits. Think loyal buyers, discount seekers, seasonal shoppers. Another option is hierarchical clustering, which builds a tree of clusters showing how data points relate at different levels of similarity. Then the second one is dimensionality reduction, which is about simplifying complex data. Imagine a data set with hundreds of variables. Algorithms like principal component analysis, or PCA, reduce those variables into fewer dimensions while keeping most of the information. This helps visualize patterns, speed up training, and avoid redundancy. Another method, TSNE, is excellent for visualizing high-dimensional data in 2 or 3 dimensions, often used to map patterns in images or genetics. And now that you know them, the applications are broad. Businesses use clustering for customer segmentation, tailoring marketing strategies to each group. Banks apply it to anomaly detection, spotting unusual transactions that could signal fraud. Scientists use dimensionality reduction to compress huge genetic datasets into manageable insights. Even in image recognition, unsupervised learning helps models discover features without needing massive labeled datasets. Strengths? Unsupervised learning shines when labels are scarce or impossible to collect. It can uncover structures humans didn't expect, revealing new insights. It's powerful for exploratory analysis, letting data speak for itself. But there are limitations. Results can be harder to interpret since there is no ground truth. Algorithms may find patterns that aren't meaningful. Clustering is sensitive to how many groups you choose in advance. Dimensionality reduction can oversimplify, discarding important information. But what if we combine methods, mixing strengths to overcome individual weaknesses? Now that's where semi-supervised learning, hybrid approaches, and ensemble methods come in. They occupy the middle ground between the categories we've seen, often producing state-of-the-art results. Semi-supervised learning is quite literally the first step. It uses a small amount of labeled data with a large pool of unlabeled data. The model learns from the labeled examples, then extends what it knows to the unlabeled ones. This is useful when labeling is expensive or difficult. For example, in medical imaging, only a few scans may be labeled by experts, but semi-supervised techniques can leverage thousands of unlabeled scans to improve accuracy. Ensemble methods take a different approach. Instead of training one algorithm, they train many and combine the results. Random forests use multiple decision trees and vote on the final answer, reducing variance and overfitting. Gradient boosting methods like XGBoost and LightGBM build trees sequentially, each correcting the mistakes of the previous one. These methods dominate competitions on platforms like Kaggle because they often outperform single algorithms. Then there are neural networks, or even the backbone of deep learning. At the simplest level, deep neural networks, DNNs, stack layers of artificial neurons to learn complex patterns. Convolutional neural networks, or CNNs, are specialized for images, detecting edges, shapes, and features automatically. Recurrent neural networks, or RNNs, handle sequences like text or speech, remembering context across time steps. These architectures power breakthroughs in computer vision, natural language processing, and speech recognition. The most powerful systems today often combine these ideas. Hybrid models might start with unsupervised pre-training, add supervised fine-tuning, and then use ensembles to boost accuracy. Self-driving cars, for instance, use deep neural networks for perception, but ensemble methods for decision-making. The benefit of hybrids and ensembles is clear. They win when raw accuracy is the priority, but there are trade-offs. They can be complex to design, slow to train, and difficult to interpret. A random forest may give high accuracy, but it won't tell you the simple why behind a prediction. In summary, these advanced methods show that machine learning is not about one perfect algorithm. It's about combining tools, choosing the right approach for the problem, and building systems that are greater than the sum of their parts. And here's the twist. These models are not at all static. Researchers constantly refine, stack, and hybridize them, chasing breakthroughs. The real question isn't which model wins today, but which unseen combination will take over tomorrow's AI. Let us know your thoughts in the comments below.